In this final example, we're going to do a triple integral again, and this time we're integrating over a portion of a sphere of radius 2 contained in the first octant. So that means that we're only using the positive x, y, and z values that are the entire interior of the sphere shape. Now, what we have to decide, we know that we're integrating in 3 dimensions. We could integrate using regular rectangular coordinates. The problem is that the bounds on the region are going to be really messy because you need to use lots of square roots for each of the bounds to be able to describe this region. So instead, we might want to use cylindrical or spherical coordinates. And the decision to make one choice or the other is up to you to a certain degree. There are certain figures that you could integrate using either cylindrical or spherical. It turns out that our math is going to be a lot easier using spherical on this because this actually is a portion of a sphere. So I'm going to represent this using spherical coordinates and set up the integration. And if you'd like, you continue watching for the integration itself. So recall, for spherical coordinates, I need to think about what are the rho values, meaning what are the possible distances from the origin for every single point that lives in the interior of this region. That's maybe the easiest one to start with, that we see that rho has to be between 0 and 2, and that's just because that's the maximum radius of this sphere, and we want to include all of the points from 0 out until that maximal radius. Next, let's think about the angles on phi. What angle is traced out with the positive z-axis? That I'm thinking as these points increase, we know that our phi value has a minimum value of 0 because that would be right up here hugging the z-axis, along the z-axis. And as my phi angle increases, this angle of declination, I want to go pi over 2 angle units, or 90 degrees, until I hit flat into the xy plane. The same thing is true of our angle theta. Theta measuring the angle that's traced out with the positive x-axis that I want to swing in a quarter circle until I hit pi over 2. Thus, the bounds for this region W are going to be really simple in spherical coordinates. Thankfully, the function that we're looking at, because in order to integrate in spherical coordinates, we also have to convert this function into spherical coordinates. X squared plus y squared plus z squared. Notice by Pythagorean theorem, that's just going to be the distance from the point to the origin squared, because rho squared is equal to x squared plus y squared plus z squared by Pythagorean theorem. Alternately, in the previous video, we had really, really long ways of being able to write out each of these coordinates. And if you wanted to, so this is an at-home exercise. You could convert these into their representations. So for example, x in spherical coordinates, as a review, is given by rho sine of phi cosine of theta. That's my x coordinate. I could square it. And then add my y coordinate, sine of phi sine of theta, squared. And then I could add my z coordinate, which is rho cosine of phi, all squared. And if you write all this out, you can see that you can factor out certain pieces and certain things will combine, and you can use the trig identity that cosine squared plus sine squared equals 1, and you will end up with the same result, that this x squared plus y squared plus z squared is in fact y squared plus z squared is in fact rho squared. So that means that the setup of our integration is easy. We have our bounds. I'm going to do it in the conventional order as theta goes from 0 to pi over 2. But by Fubini's theorem, I really can do this in any order that I want. P equals 0 to pi over 2. And then my rho goes from 0 to 2. My interior function here is v squared. But don't forget, we also need to keep track of this term of integration because we've converted our coordinate system to spherical coordinates. And that means that I need to multiply by rho squared sine of phi. And my differentials go in order phi rho, phi phi, phi theta to match the bounds of integration. So again, if you'd like, you can pause the video here. You don't have to watch all the integration, or you can continue on, and hopefully I'll be able to integrate this. I'm going to do some cheater notation and just leave these as integrals without the bounds written on to save some time until I actually evaluate the integrals. Phi rho, phi phi, phi theta. So my first step, I'm going to integrate with respect to rho, treating the sine of phi as a constant. That leaves me with 1/5 rho to the 5th times the sine of phi. I'm evaluating my rho values as rho goes from 0 to 2. Don't forget that I have my two outer integrals still. If I plug in 2 to the 5th, that's 2, 4, 8, 16, 32 over 5. Minus 0 over 5 times the sine of phi. D phi, d theta. So in our next step, let's integrate this with respect to phi. I know that the integral of sine is negative cosine. So I'm left with 32/5. I could pull this constant out front of the integration if I wanted to, times negative cosine of phi, evaluated as phi goes from 0 to pi over 2, the outer integral. So the cosine of pi over 2 is 0. So I get 32 over 5 of 0 minus the cosine of 0 is 1, so it's minus negative 1. Not forgetting the outermost integral. So this becomes just 32/5. Now I'm going to integrate 32/5 with respect to theta, and I end up with 32/5 times theta, evaluating theta as it goes from 0, theta goes from 0 to pi over 2. So that's just going to be 32/5 times pi over 2, which is equal to 10/32, or 16/5 times pi. One final comment on this, that as I got this solution, I thought to myself, this seems a little funny because this doesn't really match up with what I would think the volume of this region would be. And that's an easy error to make, that in doing this calculation, I wasn't actually finding the volume of this eighth of a sphere, right? Because volume would be when I had a constant function. And in this case, I don't have a constant function. I have a variable function, meaning at different points in space in here, this three-dimensional function is taking on a different output value. And it's taking on an output value of rho squared, meaning at the origin, this value is 0, and as I go outward and outward, you could think of this three-variable function as a set of shells that have greater and greater density as I go outward. And so I'm computing the total mass where my density is variable over this volume. And that's why the 16/5 pi is not going to be equal to the volume of this region.